Lecture 17. We'll talk about linear regression today. Suppose you have two data sets and you put them as scatter plots. So here, let's say you're shopping for external storage, and there are different market prices and different sizes. Some are like two terabytes, and some are like only 500 gigabytes. And having this, you want to know like the relationship between them, and you can draw a line that has the smallest square error. And by that I mean the following: for any data point that you have, you can draw a vertical line, right? You can draw vertical lines here, and the length squared of the vertical line can be added up to measure the total square error. And there will be one unique line that you can draw, and that's actually through calculus. You can use calculus to show that there's only one unique line that would minimize that square error, and you get this thing called the linear regression. And we can use this linear regression to get an idea of the relationship between the x and y, right? Okay, so first, when you have a scatter plot, the first kind of question you can ask is there any linear relationship between the variables? So that's the main question that we're going to ask today. And then after addressing that main question, we will talk about how to use that linear regression line. Okay, in statistics, correlation is any statistical relationship, whether causal or not, between two random variables. So we're really looking for correlation. Okay, so what is this thing called correlation? Well, as formulas, this is what you do. You remember the z-scores, right? Now, because we have the x and y data pairs, pair of numbers, right? So the example that we started with was the price versus the size of external hard drive. So the values of the prices would be one data set, and the values of the size of the external hard drive will be the other data set. And you can take their z-scores separately, right? So you take any random price that you get from the sample, you can subtract x minus x bar and divide it by the standard deviation. That's how you calculate the z-score, right? So you calculate those z-scores for each one of x and y pairs, and you can compute something called the correlation coefficient, sum of zx times zy divided by n minus 1. And that also requires some mathematical proof, but you can show that this value will always be between -1 to 1, where if that value is close to 1, then the scatter plot looks like a line. And if it's close to -1, it also looks like a line, but with a negative slope. And if it's close to 0, then it doesn't look like a line at all. It's just all over the place. Okay. So here are some examples of scatter plots with different types of correlation. And what do you think the value of r here would be? Just take a guess. Close to 1. It can't be 1. If it's 1, then it's a perfect line. Okay. So your guess should be something like 0.9 or something like that. Yeah. How about this one? -0.9. Okay. Yeah. It can't be -1. That would be a perfect line, but it's close to the line, so it would be -0.9. How about this one? It'll be close to 0 because there's no correlation between the two, right? Having a big value of x doesn't guarantee that y could be big, right? See, you could have something like here where x is relatively big, but y value is small, whereas a data somewhere like here would have a small value of x but big y. Here you have a value where both x and y are big. Here there's a value where both x and y are small. So it's all over the place. Knowing one doesn't allow you to guess the other. On the other hand, for this scatter plot, you kind of have an idea that having a big value of x means that you'll have a big value for y. Here, it means that having a big value for x will have a small value for y, right? You can see that this point here has a big x coordinate, whereas it has a small y coordinate. You can see that? Can you see that? Right, yeah, okay. So uh, for these two these two scatter plots, you do see some correlation. Here, there isn't any. Now here, this is a tricky one. This one, what do you think the correlation coefficient value of this would be?
0.
It'll still be 0, right? However, we do see some kind of a relationship, right? Yeah, so it looks like when x is near this middle point, y is maximized, but then as you get further away from that middle point, you get smaller y value. So even if your correlation coefficient becomes 0, you should still look at the scatter plot because there might be some nonlinear relationship that's present in the scatter plot, and you may not, you may fail to catch it because you're just looking at the R value. So it's always good to have a scatter plot. Scatter plot will reveal any kind of relationship between the two types of values. And even if the R value doesn't come up as significant, if it shows something like this, then you can transform this data in other means, or you can also do nonlinear correlation. So there are ways to do the nonlinear regression. There's the logarithmic regression. There's quadratic regression. Some additional topics. We wouldn't have time to explore the other types. Here we are only going to do linear regression only. But I just want you to know that there are cases, there are statistical models that can handle nonlinear relationship like this as well. All right, so hopefully this gave you some idea of what correlation coefficients do. But then how do you actually calculate them? Well, I first showed you how to calculate the correlation coefficient. How about that linear regression line? Well, here's the formula for the linear regression line. It's the formula for linear regression is y equals to a plus bx with the following formula for a and b. See, b is the slope, and it's also called marginal change. Marginal change means how much y would increase every time x is increased by a unit of 1. Okay, that's what marginal change means, which is the same thing as the slope. A is called the y-intercept because that's what it is. I mean, it's if you think about the line equation, y equals to mx plus b, right? Usually we use b as the y-intercept, but here it's somewhat reversed, right? So I was tempted to write this as ax plus b rather than a plus bx, but I was forced to write in this weird format because your calculator writes in this way. Okay, so you'll see. We'll later use the calculator to do this. So I haven't made up my mind whether to put actual questions regarding using this formula because you can actually calculate it using the calculator. I'll later come back to this one and give you more examples if I do intend to put this on the exam. Okay, but what's really important is that when you're given a linear regression formula, you have to be able to figure out which one is the y-intercept and which one is the slope. Of course, the one that's multiplied by the x is the slope. And also, sometimes the question might be asking for the marginal change, and you have to know that marginal change means the slope. So it's the same thing as b. Okay, so those two are the important things. Okay, the intercept, knowing which is the intercept, which is the marginal change. All right. Now, once you calculate the r value, then the immediate question you get is, how large does r have to be to say that there is a relationship, linear relationship between the two variables? Okay, and that actually depends on the size of your data. So loosely, it's like this. I do see that this is highly correlated, right? But if we had the same kind of scatter plot, and I think this is more like about 20 data sets, if I only had like 5 points that looks like this, I might be less tempted to say that there is a correlation, because you might have if you only have data set of 5, then the scatter plot might look linear just by chance, don't you think, right? Whereas if you have many data, like 20 data sets, and you still have something like this, then I'm tempted to say that there is a some relationship between the two. So the question that we want to address is the following. Is there a significant correlation between the two or not? Okay. So to address this is called the Rho test. And let me explain how to do the Rho test. And we are going to do the same 4-step test, just like how we did the other hypothesis testing. So step 1, you have to set up the hypothesis. And for the Rho test, the null hypothesis is always rho equals to 0. Okay. Not only it has an equal sign, it has to be 0. Okay. Rho equal to 0 means that there is no correlation between the two. Okay. And H1 would be that there is some correlation. The alternative hypothesis would be that there is some correlation. And the reason we're using the rho, see, RHO is this letter right here, that the thing that looks like a P, but it's actually a Greek letter R. And we are using the Greek letter for population values, right? So when we say rho, that's the R value, the correlation value of the entire population. Whereas the letter R is used for the correlation that we get from the sample. So as usual, when we do hypothesis testing, we only have access to the value that you get from the sample, whereas you want to draw a conclusion about the entire population's value. So we want to know whether rho is 0 or not by calculating the R. And of course, if R is significantly close to 1 or -1, then we would reject the null hypothesis. But the question is, how significant should it be? How large should it be, right? Okay, so that's step 1. Now, step 2, what's step 2? Do you remember the step 2 of 4-step hypothesis testing? Yes?
Critical value.
Critical value, yes. You have to find the critical value. And to find the critical value, you have to use the Rho table I handed out in today's lecture. And to use that, you also need the degrees of freedom. And internally, it does some kind of transformation of the R value into some test statistics. But you don't have to know that. What's really important is that when you use the Rho table, the degrees of freedom should be n minus 2. Now, why n minus 2? That's because we're trying to think about the data as whether it's close to a line or not. But line has two things, right? It has a slope and the y-intercept, right? So because a line uses up 2 data points, it loses 2 degrees of freedom. Uh, yeah. So anytime you use some information from the data, then you lose the degrees of freedom. So for the t-test statistic we were using, for the t-test, the degrees of freedom was n minus 1, right? Over there, we subtracted 1 because we were using the sample standard deviation as a replacement for the population standard deviation. So we were using 1 information from the data, so that's why we subtract 1. Here we're trying to think about a linear regression line which is using up 2 data points. So degrees of freedom here is n minus 2. This degrees of freedom is a bit hard to understand. So you just have to remember them from example to example. Okay. All right. So once you have the degrees of freedom, then you look at the row table like this one, and then you can figure out which one it is. So for example, if you had 8 data points so that your degrees of freedom is 6, and then you're going for, say, significance level 2%, then if the rho value, or R value that you calculate is 0.7887 or bigger, then you say it's significant. Okay. All right. So then we have the step 3, calculate the test statistic using this formula, and then step 4, we draw a conclusion. And one thing that you have to be careful is that, the correlation coefficient should be negative. So when you compare with the critical value, you have to take the absolute. Okay, so if you have a negative value, then you take the absolute value, make it positive, and then see if your R value is greater than the critical value or not. Okay, if it's greater than the critical value, then you say we reject the null hypothesis. All right, so we'll do an example, and when we follow this with the example, it should be easy to follow. But I also want to say that in practice, when you're given the table of values, we will, rather than using this formula, we will just use the calculator and let the calculator calculate everything for us. So what we're going to do is we're going to do this linear regression t-test of TI calculator, and we just we'll enter the variables x and y values in L1 and L2, and then use this linear regression t-test to calculate everything that we need, the A and B and statistic, p-value, correlation, and all that. Okay. All right. So let's do an example. I'll show you how to do it by using an example. All right. So suppose we have the following data. Okay. Now we're going to do second list, and we're going to edit. Oh, I think we have to do stat and edit. Yeah, stat and edit. And then in L1, I'm going to type in the values: 4.5, enter, 10.2, enter. I'm just going across. Right? So chocolate will be our X value. 4.4, enter, 6.3, enter, 2.0, enter, 8.5, enter. Is that all? Yeah, that's all. Okay, so we have 6 data points. Now let's move on. Scroll to the right. So type, punch this key right here, and go to the right. And now we enter the L2, 5.5, 24.3, 8.6, 9.0, 1.9, 25.3. Okay, so we have the number of kilograms of chocolates eaten per person per year. Yeah. I wonder what United States average is. That's a lot of chocolate. Okay. And then you have the second data point where you have the Nobel Prize. Okay, now let's quit. And you go to stat, and you go to test, and you scroll down, and you look for linear regression t-test. There it is. Okay, linear regression t-test. You enter this. And it's already given as L1 and L2. Now, the linear regression test also has the left tail and right tail if you are sure that you're looking for a positive correlation or a negative correlation. But in this class, we'll only do the two-tail test. So we will never change this. So nothing here should be changed. All we do is just calculate. So always put your x values in L1 and y values in L2. Don't change anything. Just execute this. And see this, y equals to a plus bx. I really wanted this to be ax plus b, but it uses this, so I had to follow this one. Okay, so y equals to a plus bx, where the value of a is negative 6.2218, right? And then we have p-value is 0.005, very small. Okay, and then b y-intercept is 3, and we have values for s and r squared. And what's important is this r value. The test statistic is r equals to 0.9408. Okay, so let's type some results here. So we have r equals to 0.9408, and the linear regression was, what was it? Negative 6.22 plus what is it? 3.112. Yeah. Okay, x. So that's the linear regression line. Okay. Okay. Now, what's not given here is the critical value. So let's think about this one. To get the critical value, first we have to figure out the degrees of freedom. What's our degrees of freedom? N minus 2. We have 6 pair of data, right? 1, 2, 3, 4, 5, 6 pair of data. Yes. So the calculator also tells you the degrees of freedom as well. So it's 6 minus 2, n minus 2, right? Which is 4, and that agrees with the calculator, right? So we have degrees of freedom equal to 4, and our significance level is 0.05, right? So what you do is you have to go to the table, 0.05 with degrees of freedom 4, what is it? 0.8114, right? So that's what you need to put. Just a minute. R critical is 0.8114. Yes, you have a question?
Yes, how did we know that the alpha was 0?
How the question is, how did we know that alpha is 0.05? How do we know that? It says right here, 0.05 significance level. Okay. Yeah. Any other question? So we know that our critical level value is 0.8114. And indeed, since the test statistic is greater than 0.8114, what can we conclude? We reject the null hypothesis, which says that there is no correlation, and yeah. So we have sufficient evidence to show that there is a correlation between the amount of chocolate consumption and the number of Nobel laureates. Okay, that's kind of funny, right? So, does this mean that in order to have more Nobel laureates, you should promote chocolate consumption? Should this be the next advertisement of Nestle? Yeah. Uh, Now, however, that's what's really important is that, but remember, correlation does not mean causation. Have you heard of this before? Correlation does not mean causation. Some of you may have heard it. Yeah. Yeah. Having a correlation does not mean one is causing the other. Okay. It doesn't mean that chocolate consumption is going to uh, produce more Nobel laureates, nor does it mean that having more Nobel laureates makes the citizens of that country to consume more chocolate. Uh, it's just correlated somewhat. Okay, and what you have to be very careful about when doing linear regression is that sometimes people just get correlation out of random chance, and they're like, "Wow, there's something going on here," and they think one is causing the other, and that happens a lot in health research. Right? You might have, like, let's say, a popular drink is a new fad, and then you also see increase in certain type of cancer, and then you might say, "Hey, this drink may be causing cancer." Yeah, you could have that, which later could turn out as not true. Of course, you should investigate if that correlation is really a causation, but to actually prove that a correlation is a causation, you would need further testing. Okay, uh, and there are some other reasons too. Like you might say something like, uh, for some reason, you would expect that places that are rich nations will produce more Nobel laureates, right? And rich nations would also consume more chocolate because they eat more. So if you go by that logic, maybe there's a completely separate reason why one causes the other. So uh, just having what we are doing here by the Rho test is just showing that there is a correlation. Just showing that the R value that we get is high enough to say that there's a correlation. But you cannot say beyond that. Okay. So that's a very important concept, and I might ask you this in a slightly different wording or context, but you should be aware of this. It's kind of important. Okay. All right. Now, so hopefully that was was something that you're used to, because it's really nothing different than our hypothesis testing, right? Step one, H0 will be there is no correlation. H1 would be there is correlation. And then you have to find the critical value, and then you use a calculator to find the test statistic. And once you know that it falls in the rejection region, you reject the null hypothesis. So apart from the part where we use the calculator, what we're doing here is nothing different than hypothesis testing. However, when it comes to correlation, linear correlation, there's one thing that we can do in addition to just hypothesis testing, which is that we can make prediction. Okay? See, this relationship, if it's valid, then what it tells us is that if we know the value of x, then we can predict the value of y. Okay? That's interesting, right? However, that it comes with a warning. If the R value, the correlation doesn't come out as significant enough, then we should not use this. And we should just use the average value as a prediction for Y. So let me give you two examples to explain what I mean. So back to our example, we found that chocolate consumption is correlated with the number of Nobel laureates, right? And you can ask this question. You have another country, and you looked at their average chocolate consumption, and the average is 5 kilograms of chocolate per person per year. And the question is, can you guess how many number of Nobel laureates there are per million people? Then, because we did find that the Rho test was significant, there is a correlation. We can use y equals to a plus bx to actually calculate the y value. So what we can do is we can take this equation, plug in 5 into this equation, and you get 9.33. So your answer is, oh, I think we have 9.33 Nobel laureates per million people. So that will be your answer. Oh, by the way, if you're curious about that previous example where we did come out as significant, if you add more data points, you'll find that it's not correlated. So the data that we gathered somehow by chance had some correlation. If you gather more countries, then it will show that it's not true. Yes, you have a question?
Why does it use a t-test?
Oh, in the handout, I have so someone is asking me for the formula about the t-test in the handout. That's just a note in explaining how the p-value is actually computed by the calculator. We will never directly use that formula. Okay. Right now, if you're following the handout, we're actually in the back page. And we're doing the number 3, we're using regression line for prediction. And I'm right now explaining the case 1. Okay, so that's our prediction. And that's the main strength of linear regression. Not only you can say that there's a correlation, you can also have a prediction that would give you some ballpark estimation of what the value, y value would be if you know the x value. Now here's a second question. In a sample of 8 men, their shoe size and weight were measured. The average shoe size was 9.5 inches and the average weight was 182 pounds. The regression line had formula y equals 90 plus 10x. The correlation coefficient was r equal to 0.57. If another man shows up and his shoe size is 11 inches, what is his predicted weight? Okay. Now, if this linear regression was valid, how would you predict? So here's what's happening. You would expect that bigger shoe size usually means bigger person, and bigger person would mean heavier, right? So uh, we know that on the average adult men in this sample, 9.5 was the average shoe size, and average weight was 182 pounds. Yes.
So would you plug in the 11 inches for X?
Yeah. That's the correct thing to do. So if we know that this is valid, then what do? We plug in 11 in here. 11 times 10 is 110 plus 90. That will be 200. So we would deduce that this person must have 200 pounds as the weight, right?
11 is the row.
Huh?
11 is the row.
No, 11 is the X. See, we have two types of data, right? The shoe size is X, and Y is the weight, right? So we're not given the actual table, so we don't know the actual values, but we know that the average value for X is 9.5 and the average value for Y is 182. And then we have this linear regression. Okay, so if you plug in 11, you would get 200. However, here's the question now is this linear regression valid? Is this linear regression line valid? Now, which test do you use to say it's valid or not? Huh? Rho test. We use the Rho test, right? And our R value is 0.57. How do we know if this is significant or not? You have to compare with the critical value. Okay, so right now what you need to do is, what's our degrees of freedom? 8 minus 2, which is 6, right? And then you go to the regression table, you go to 6, and, I think I forgot, sorry. Okay. I forgot to state the significance level. So use 0.05 significance level. Okay. I forgot to add that to the note as well, so please put that somewhere. Okay. So if we have degrees of freedom 6 and alpha as 0.05, let's go to 6 and 0.05 is 0.7067. 0.7067. Okay. So we know that critical R is 0.7067. I forgot the value. Just a minute. Where is it? Yeah, 7067. Okay. Now, so what do you think? R value is 0.57. Critical value is 0.7067. So is our R value significant? No, it's not. So does this regression line have a meaning? No, we can't trust it. Okay, so that's not meaningful enough. So the R value is not significant. Therefore, we cannot use this. Okay. Now, if we can't use that, what's our best prediction then?
What makes it not significant?
What the question was? What makes it not significant? Well, it's not significant because our R value is under the critical value 0.7067. The bigger the R value is, the more significant the correlation is, right? So this Pearson Rho table gives us what value to use to say if it's significant or not. And it's saying that for sample size of 8 men, anything under this value can be just by chance. Okay, yeah. You could get some high correlation like 0.65 just by chance. So you can't really say that the data is saying something. Okay. All right. So if the R value is not significant, what do you say? We cannot use Y. So what else should you use? Should you say that the guy must be 100 pounds? What's your best guess at this person's weight? The average. That's the best you have. Okay? If you don't have any means to come up with the best guess, your best guess would be the average. That's the logic, right? Does that make sense? We can't use this, so what's the best guess? 182 pounds. Yeah. Therefore, we have to use the average as the best guess. Okay. So that's why uh, the answer should be 182 pounds. Okay. Okay. Um, Now the last topic for this unit is the coefficient of determination. R squared, which is the value of r squared, small r squared. So you take the correlation coefficient, you square it. This is called the coefficient of determination, and it is the percent of variation of y explained by the regression line. For example, if a data strictly follows a single line of positive slope, then r would be 1, and r squared would be 1 squared, which is 100%. Okay. Yeah, in this case, the variation of y is fully explained by the regression line. Okay. Uh, so formally, not here. What did I do here? Oh, here. Okay. Formally, r squared is this value, variation explained by regression, and the entire variation. And the value 1 minus r squared would be percent of variation not explained by the regression line. So how do we say this? If the r value, the correlation coefficient r value is small, then your scatter plot will be all over the place, right? And if you ask, why do these values are vary so much? Then the answer is, I don't know. We can't explain, right? However, if the correlation coefficient r is big, then the values are following this line. And then if you ask, why does y vary so much? Then you can say that, oh, that's because x varies such and such, and you can explain the y's variation by the x's variation. Okay, and if it's completely a line, then you can say that y's variation is completely explained by the variation of x. And that's what it means. Okay, so here's our last example. Let's talk about this question. The following table shows data of repair costs of a vehicle crash at 6 miles per hour for the type of crash. Okay. So you have different cars. Some cars are pretty expensive. Like, I don't know what this one is, but I guess it's something like BMW or something, right? Yeah. If it crashes, it costs a lot, arm and a leg to replace, okay, fix it. Whereas you have some cheap models like this one, or maybe this one, okay. Yeah, it's still like thousands of dollars. But so if you have a front end crash in 6 miles per hour, you would need $978 to fix it. Whereas for the rear end, it will be this one. Okay. And you want to know if there's a relationship between the front end crash repair costs and rear end crash repair costs. And you want to know the correlation coefficient. And the first question is, what is the correlation coefficient? Is it significant at 0.05 significance level? And I want you to take some time to put these numbers into your calculator and come up with the answer, okay? So try it now. So you go to Stat, Edit, put in values. List 1 would be the front end cost. List 2 would be the rear end cost. I'm giving you a head start, so you should answer before I do. One thing that's nice to know is that if you go to L1, if you put to up arrow and go to L1 and clear, enter, then it deletes the entire thing. Okay. So go clear and then enter, it deletes the entire thing. Okay, 936 978 2252 1032 3911 4312 3469. Okay, that's everything. 1480 1202 802 3191 1122 739 and then 2767. Okay. All right, so we are done putting all the data in. What do we do? Stat, and then what do you do? Test. And what do you look for?
Line regression t-test.
Yeah, linear regression t-test. Okay. Go all the way down. Calculate. All right. So, is this significant? You see your R value? R is negative 0.08.
No, I didn't get that. That's completely different.
You got. Oh, really? You got different? Okay. Okay, so let me quit. Maybe I made a mistake in the list. So stat, edit. Let me check. 9369782252103 Oh, 3911. That's my mistake. 3911. Okay. 43124. Okay, good. And then 1480 1202 802. Okay, sorry about that. I made a mistake. Yeah, so I guess you should always check your data input. Let's calculate. All right, so what did you get for the value of R? Negative 0.282. Is that what you got?
Yeah.
Great, okay. And then we have the p-value is 0.5, so what do we do? P-value is 0.539. So is that an unusual event or a usual event?
Unusual.
It's a usual event. Because if you have something that comes up with very low probability, 0.001 or something like that, then you would say it's unusual, right? When do you say some event is unusual? If the probability is lower than? No. It's lower than? No, it depends on the question. It's if it's lower than
Oh, the R significant.
the alpha value, your significance value, okay? So our significant value is 0.05. So we would call an event as unusual if the p-value is lower than 0.05. But is it? No, 0.5. 0.5 means it's something that could occur, right? So you, in other words, the R value that we achieved is nothing special. It's like this could happen just by chance. So this means that okay, so the correlation coefficient is negative 0.282. What was it? 2826. And it's not significant because p-value is bigger than 0.05. Okay, so that's what we can say. Right. I would say thus the correlation is not significant. Okay. All right. Second, predict the price of rear end crash if front end crash of the same model is $1,200. What should we do? Yeah, see, because the correlation coefficient came out as not significant, this a plus bx with a and b values is meaningless. These two is not what we should be using. Instead, you just have to find the average of the L2. Okay, how do you find the average of L2? The list 2. You go to stat and you have to do, I'm not so sure if two variable stats also does it. Let's see. Yeah, I should have checked it before. Oh, here. Okay, so we have y bar, right? Y bar is 1614.71, right? So the answer would be 1614.71 because that is the average of the y. Yeah. So let me repeat what I just did. So what do you do again? You go to stat, calculate two variable stats, and what it does is it will calculate the average of the x and y separately. Also, it will calculate the standard deviation for x and y separately right here. You have a question?
Well, the first one, why are we not comparing it to critical value?
Oh, the question was, why are we not comparing with the critical value? We could. The answer is we could. It's just that when it comes to hypothesis testing, there are two methods, right? One is finding the critical value and comparing the test statistic, which is called the traditional method or the four-step method. The other method is to use the p-value. I'm just taking a shortcut because p-value is already with us. Okay. Now you could use the critical value if the question is asking you to use the four-step method. Then you do have to go back and use the critical value. What is it? In our case, the data points are 7, so degrees of freedom is 5. So let's see, degrees of freedom 5 and 5 with 0.05, it will be 0.7544, okay? But negative 0.24, if you take the absolute value, that's 0.24. No, our 0.7545. Sorry, where are we? Here. R critical is 7545, and R is negative 0.28. And if you take the absolute value of that is lower. So this is another way to say that, to show that correlation is not significant. Okay. All right. So going back here. Sorry to go back. So that was to come back to this question. We have to use the average. Y bar is used because the correlation is not significant. Okay. All right. Now, finally, what percent variation in the rear end crash repair cost is not explained by the front end crash repair costs? And you see what I'm saying? This is asking how much of the variation in Y is not explained by the variation in X. And what is that called? That's called the it's the 1 minus of the coefficient of determination, okay? Yeah. So you have to use the coefficient of determination. So you have to do 1 minus R squared. And that one we have to go back to our linear regression test. And if you go way down, it gives you the R squared, right? R squared is 0.0798. So what is that? That's 0.9202. Right. So 98%. No, 92%. Okay. So in other words, most of the variation in the rear end crash repair cost is not explained by how much the X is changing. Okay. So that's what it is, right? Okay, so that's everything for today. Hopefully that made sense. We'll do some more examples.